Okay, and welcome back to Calc 3. This is part 2 of the surface integral section. And we're going to look at a special type of surface integral known as a flux integral. Yeah, flux integral. So first, let's do some quick review. So you've already seen that if you've got a function f defined on the surface, and let's say the function is just a 1, then the surface integral, so there's a 1 right here. That's just going to give you the area of a surface. It's a baby surface integral. Don't forget that ds does involve that yucky looking surface area element with a big old radical. Okay, on the other hand, if you've got your surface set up and they gave you a density function, then you can do a surface integral that would represent the mass of that capping surface. And we just did 3 examples of that. Okay, so I'm done. So in order to do the special type of surface integral known as a flux integral, we need to do some preparatory work, okay? So, so what about these flux integrals? So flux is the amount of something, electric field, bananas, or whatever you want, passing through a surface. Well, I don't know, it's kind of hard to imagine bananas passing through a surface, but you can use your imagination, right? And so the total flux depends on the strength of your field and the size of the surface it passes through, and something called an orientation we're going to look at. So you just want to think of flux as the amount of something crossing a surface, where the something can be water, wind, electric field, bananas, pretty much anything you can imagine, okay? Math books will use the abstract concepts like electric fields, but that's kind of hard to visualize. So I think bananas are more fun. And so anytime you're doing a flux integral, just think bananas and you'll be good, right? The amount of bananas passing through the surface. Yeah, it's much more fun anyways to think about bananas than electric fields, which, yeah, it's hard to visualize. Okay. So we do have to talk about something known as orientation of the surface. So let's take a look at this. It's kind of weird, but what we use is we use unit normal vectors, remember N? Yeah, unit normal vector. And it's going to be normal to your surface or orthogonal. You're going to use these little normal vectors to induce what's called an orientation to your surface. Well, how's that going to work? Well, just stay with me here. You'll see shortly. Okay. So the way I like to think of it is, let's say you had some surface like this. That's a capping surface. You can use a lot of little unit normal vectors that are sticking outward like this to orient your surface. Okay, let's define what an orientable surface is. A surface is called orientable if a unit normal vector can be defined at every non-boundary point of S in such a way that the normal vectors vary continuously. What the heck does that mean? If it is possible, S is called an oriented surface. Well, now let's try to put it to you in terms of English. Okay, here's the key. An orientable surface has 2 distinct sides. Okay, like if your surface is a closed surface like a sphere, then the sphere obviously has 2 sides to the surface. It's got the outside of the sphere, here's a sphere. You've got the outside, and then you can get inside the sphere and you can be inside the sphere. So it's got 2 distinct sides to the surface. Now you may be thinking, well, all surfaces have 2 distinct sides. Well, that's normal to think that, but it's not the case. Look at this piece of paper here. I claim a piece of paper definitely has 2 sides. You can have these little unit normal vectors on one side of it. They're all sticking up. And then on the other side, the flip side of the paper, you've got all the unit vectors pointing down. So this piece of paper, the way it looks right here, where it's not folded or twisted up or anything, clearly has 2 distinct sides. So that piece of paper definitely would be an orientable surface. This sphere would be an orientable surface. Do all surfaces have 2 distinct sides? No. There's something called a Möbius strip that doesn't have 2 distinct sides. Möbius strip. So I want to show you a Möbius strip demo here. Check this out. Yeah, cool, huh? That's a media strip. Well, I don't get it. Well, I want you to keep your eyeball on the arrows, okay? And the arrows are going to sort of swing around. They're going to start on one side of the media strip, and they're going to kind of wind all the way around. And you'll notice they're going to end up on the opposite side. And you can actually make a media strip at home. Just take a piece of paper and take a strip of it, like tear off a piece of paper in a long rectangle, and then do a half twist, and then Scotch tape the two ends together. And you'd have a media strip. So watch closely. You start on one side, and then if you were thinking of a bug that was the arrow could be a bug walking, the bug will end up on the outer side of the strip. And then as it goes around the outside, it comes around, and because of that one twist, it'll end up on the opposite side. So media strips are kind of cool in that they are not orientable. They do not have two distinct sides. Pretty cool, huh? Now, we're going to deal with surfaces that have two distinct sides. We're going to not deal with media strips because they are the exception. Okay, but they're kind of fun, don't you think? You guys having fun yet? No. Okay. All right. And we'll see a meme here in a second. Check out this meme. It should be in your course reader. So here's somebody who made a media strip. They took a piece of paper and Scotch taped the ends to it. And what I love about this meme is teacher said we were allowed to bring a single side paper for notes. Ha 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 ha. Get it? A media strip doesn't have two sides. So he's doing his notes on both sides. Because a media strip, both sides are the same side. You guys should be laughing right now. Come on. Thank you. You guys, come on. Have a sense of humor here during this shortened week. Okay. So we're going to use the gradient. You guys remember the gradient? To find a unit normal vector. So here's your capping surface equation. Z equals little g. And let's have it be an orientable surface. That means it's not going to be one of those cool media strips. Sorry. It's going to have two distinct sides. Then you're going to rewrite it. And you've done some rewriting in a previous module when we were finding gradients in order to find tangent planes. I don't know if you remember, but it did matter which side. It didn't matter which side you got everything on. You want everything on one side and zero on the other. And so we're going to rename this big G. And so the gradient is going to be the big normal vector will be the unitized gradient. So del G, and we'll unitize it. So we'll divide by its magnitude. So what is this going to look like? Well, if you take the partial of z minus little g of xy with respect to x, there's no x's in the little z, so that's 0. And then you'll have minus whatever the partial of little g is with respect to x. And then if you take the partial of big G with respect to y, you'll end up with negative the partial of little g with respect to y. And then when you take the partial with respect to z, you'll just get 1 because the derivative of z with respect to z is 1. And if you unitize this, you guys know you're going to have to divide by the magnitude of this vector. Now, this is a unit normal vector where it's oriented up. Why? Because the z component is a positive number. So these ends, like if you look at my piece of paper here, it would be these ends here that are pointed upward. We're orienting the surface with those ends, all those little itty bitty ends. Now, what if you wanted the opposite side of the surface? No problem. So you could also say, well, I want the opposite because I want to have it pointed down. Okay, and sometimes you need the one pointed down on a quiz or an exam, you'll see. So what does that mean? We just take the opposite in sign of everything. And you'll notice that now the z component is -1. That's how you know it's pointed down. And the magnitude is still the same. It's going to be this horrible looking radical. Okay. And this is the unit normal vector that we would say is oriented down. And normally when we do some problems, we'll have the oriented up. That's more common. But sometimes you do need to take the ones that are oriented down for certain problems. Okay? And back to the mean. Here's a sheet of notes, single side. There is such a thing as a sort of a 3D version of a media strip. It's known as a Klein bottle. There's a picture of it. It's kind of cool. Supposedly, this only has one surface. It doesn't have two distinct surfaces. It's got no boundary. You can read about this in Wikipedia. It's kind of fun. The non-orientable surface. We won't be dealing with Klein bottles. I'm just trying to give you a full-blown education in this class. All right, full-blown education, so you know everything. That's right. So now let's get to the flux integrals. So where we're going to have a certain amount of bananas passing through a surface. Yeah, that's right, bananas, or whatever you want. Okay, so one of the big things about this vector form of a surface integral, you can think of it as relating to the flow of a fluid through a surface S. If you prefer the flow of bananas, I'm okay with that too, whatever is your pleasure. And these kind of integrals are known as flux integrals, but they are surface integrals, okay? They're special cases. So we're going to see that, and then we'll get into it and we'll do an example. So if you imagine this surface here submerged in a fluid, having, like a jacuzzi, and let's say you've got your velocity of all the water in the jacuzzi given by this vector field. If you pick a small little patch on your surface, delta S, over which your force field is about constant, then the amount of fluid, or bananas, crossing your region per unit time is approximated by the volume of that column. Like if you set a stopwatch and you went, okay, go, stop. And then you would look at the total amount of bananas or water that flowed across that little patch per 1 second, or whatever your time unit was. So that volume would be the height. And that height is the projection of the vector field onto the unit normal vector. So you're going to have this F dot N. That's the projection, involves dot products. And then the area of the base of that little weird looking kind of, it looks kind of like a rectangular box that somebody kind of slanted over a little bit. The base is delta S. So the total volume of fluid crossing your surface S per unit time is called the flux of F across the surface S. So now let's officially define a flux integral, which is just a special surface integral. So you first going to have a vector field. The components are M, N, and P. Your book may call them something else. I think your book likes to call it F, G, and H, but I don't like that because we have enough F's and G's running around. We don't need more. And assume that M, N, and P have continuous first partials on the surface. And let's say it's oriented. It's an orientable surface. So you have these unit normal vector N. So the flux integral of F across S, the flux, is equal to this special surface integral. And you know it's a surface integral because you got a big old S here. That's how you know it's a surface integral. And then you also have this surface area element here, which you all know what it is, but it's going to turn out, you don't have to worry about that. So when you evaluate your flux integral, you're going to be given a surface. Then you're going to, you could, but you're not going to need to, in order to just sort of step you through this penumbra, if you will, of hand waving to get to where we want to be. If we rewrote this surface in a more generalized representation where we got everything on one side and zero on the other, then del G, which would be the gradient, which would be orthogonal to the surface, we want the unitized version of that, which we call N. So you're going to get your del G, your gradient, divide by the magnitude, times your ds. So we're doing this part of this flux integral. So watch closely because it's going to turn out a whole bunch of stuff cancels and you never have to even get big N. Okay, something nice. So this surface area element, you remember, looks like that. It's your surface area element. But wait a minute, that surface area element, that radical exactly matches the radical of the magnitude of the gradient for the surface. Yeah, so they cancel. All right, woohoo. So what's the only thing that's left? Your gradient, dA. That's right. Which is, if you use the oriented up version over here, and back. Where is it? Oh, too many memes. Too much fun we're having. Yeah. Woo! Oops, too far. Stop. Stop. It's this right here. Now notice you have some negatives there. And so you don't want to blow this because this is going to be worth half a letter grade on your final. So don't blow those negatives. This is for when you're using your flux integral and you want to find the amount of bananas passing through your surface with an upward orientation. So the bananas are flying up, up and out, flying bananas. So what you're going to end up having when you're doing one of these flux integrals is you're going to have the negative little gx, negative little gy, and positive 1, because that's upward. Okay, now let's do, how do you evaluate a flux integral? Because, you know, you're going to be given one of these, and it's like, oh no, that looks really scary. Ooh, I know. You're going to turn it into a regular integral where you're integrating over a region. They'll either give you the region, or you can assume it's the projection of your capping surface onto the xy plane. And you're going to take a dot product of the vector field with this negative little gx, negative little gy, 1 dA. And that's if you are asked to figure out the flux where you're orienting your surface with upward oriented vectors. On the other hand, if they do ask you to give the flux for oriented downward, because they might, no problem. Just take the opposite in sign. So you'll have positive gx, positive gy, negative 1. And so this is the flux for oriented downward. Okay, so whatever they ask, you know, make sure you follow directions. Okay, there you have it. That's how you evaluate one of these flux integrals. Yikes. I know, that looks really scary, doesn't it? Wow. All right, so are you ready for your very first flux integral where you're going to figure out the amount of bananas passing through a surface? Or the amount of water or whatever. Okay. Take a look at this surface. It's part of a paraboloid, and you don't have to graph the surface, but I like this one because it's a downward facing paraboloid, and they want the positive part. So the part that's above the XY plane. So that's the paraboloid. Okay, it's a nice capping surface, and it's clearly orientable. It has two distinct sides. It has the outside and the inside. So fine. So they gave us z, which is little g. So let's go ahead and get those partials. This is pretty easy to do. I get the partial with respect to x is negative 2x. The partial with respect to y is negative 2y. So your flux, which is considered this funny looking surface integral. I know, write it down. Get used to it. F dot n ds. We're going to turn it into a regular integral. So we're going to have a region R. And you're going to take the vector field, which I'll write down in a minute, but not yet. And you're going to take the dot product of it with the opposite of gx, so negative, negative 2x, the opposite of gy, so negative, negative 2y, 1. Now, I am going to need to do a dot product, and so I'm just going to copy down the vector field they gave me, but I hope you noticed something wrong. What is going on that doesn't look so good? What did we say about a z appearing in a double integral? Remember, that's not good. No bueno.
Yep, we got to replace z.
Yes. With what? Ah, well, they gave you the z, the capping surface. 9 minus x squared minus y squared. So we know what to replace it with. Okay. So let's go ahead and replace that z with the surface, because you're only allowed to have x's and y's in a double integral. And flux integrals are double integrals, not triple, okay? Unless they're doing a closed surface. We're not doing that yet. Okay, now it's time to actually go do that dot product. You know, 3x times 2x plus 3y times 2y plus 9 minus x squared minus y squared times 1. I know. It's like, oh, man, I never give myself enough room. Why not? If I did, I think my course reader would be 1,000 pages long. It'd be nuts. So I'm going to have 6x squared plus 6y squared plus 9 minus x squared minus y squared, like this. Let's clean this up by combining like terms. I've got some x squared terms. Yeah, let's add those together. I got some y squared terms. Yeah, let's add those together. And I got the plus 9. Okay, fine. Now, I hope that you can see that converting to polar is going to be a good idea. Do we always convert to polar every time we do a surface or flux integral? Absolutely not. Oh, no. Only if it makes sense to convert to polar. Come on. Well, why does it make sense for this problem? Well, look. The capping surface does cut into the xy plane. So if we want to discuss what that trace is found by setting the z equal to 0. And then you'll find out where that paraboloid cuts into the xy plane. So if you substitute a 0 in place of z into that paraboloid equation and then rearrange the equation, I think you'll see that, aha, it's a circle centered at the origin of radius 3. So here's your region R. So you know, convert to polar. Because if our region is a circle or a portion of a circle, we're going to want to convert to polar. No way do I want to do that in rectangular coordinates. I'm not crazy, okay? I may look crazy, but I'm not that crazy, okay? Okay, so you know the first two terms here, if I factor out a 5, then this will convert to 5r squared. So here is what it looks like is happening when I convert to polar. And then you know the area element, be a pirate, r dr d theta. And let's distribute the r before we go ahead and integrate with respect to r, so we don't blow this. And this is a pretty easy integral. There's nothing special here to do. What do I have here? 5/4 r to the 4th plus 9/2 r squared, going between 0 and 3. And it looks like I'm going to get some really weird number here. It turns out that that is 405/4 plus 81/2. And if you use your graphing calculator, this ends up being 567/4. Fine. And then the last integral, you're just doing a 1 with respect to theta. And that's easy because it's just going to be theta going from 0 to 2 pi. And then you know, reduce. So your final answer is 567 pi halves, and that's approximately 890.6. So the total amount of bananas, the flux, through our surface is given by that number right there. Okay, that's flux. Total amount of fluid or total amount of bananas or whatever. So to recap, what the heck was this? What did we do to do the problem? So they asked us to find a flux. They gave us the surface that we're finding the amount of bananas that's passing through the boundary. And then they gave us the vector field. That's the velocity of the bananas, flowing through the air. And then we ended up having to do a dot product of F dot product with the gradient. That's del G. That's a gradient. And you're taking the dot product of your vector field with that gradient. And don't forget, if your vector field happens to have any z's in it, sometimes it doesn't. But if it does, you're not allowed to have any z's in a double integral. And flux integrals are double integrals when your surface is not closed and our surface isn't closed. So you always replace your z with the capping surface equation, which has x's and y's in it. And then after you do your dot product, you may or may not have to convert to polar depending on the region. And we had to because our region was a circle. And we got our answer. Okay. And that concludes that example of flux. And that is the only example I'm going to do for flux for you. You got to do some homework and you'll get a chance. Let's do some true false problems and we'll wrap this lecture up. So true or false, explain why or why not. If the surface S is given by x going from 0 to 1, y going from 0 to 1 z equals x, that looks like it's a portion of a plane to me. Then this surface integral is going to be, you know, dx dy, we have 0, 1, 0, 1, that looks good. Fx, y, x. Does that look true or false? This is a little tricky. I'll give you a hint. Is that ds just equal to dx dy?
False.
Yeah, that's false. And the reason why is because ds is equal to, you know, this horrific radical, and they forgot to include that in converting this surface integral to a regular integral. So the little g here is simply x. So the partial with respect to x is just 1, and then the partial with respect to y looks like 0. So this looks like square root of 2. So in order to fix this, we did want to make it true, what it's missing is a factor of 2, square root of 2. So if we would put the square root of 2 in there, then it would have been true. But because it was missing that, it's false. Cool, huh? Letter B. Suppose you've got a function that's continuous on a smooth curve, and the curve is parameterized by some vector valued function where time goes from a to b seconds. Then this line integral, remember this is a scalar line integral, you should be familiar with that. Well, we didn't cover scalar line integrals in this section. We were doing flux integrals. I know, but this is kind of review. We're doing a lot of weird integrals in this chapter. Is this legit? Turning it into a regular integral. And I claim false because ds is the arc length element, not the surface area element. That's big ds. That's different. Big S here is surface area element, not to be confused with little ds. Really? There's different uppercase and lowercase s? Yes. Don't confuse these. Big S means surface. Little s means arc length in mathematics. Ooh. So what is the arc length element? Do you remember that it's the magnitude of the velocity vector? So if you did get the velocity vector for this particular vector value function, they didn't give us much to go on, but that's going to be the square root of the sum of the squares of that velocity vector. Yeah. And then you'd have a dt. But look what they have here. Where's that extra 1 coming from? I think they're confused. They're getting that extra 1 from the surface area elements. And this person is very confused. So you want to make this true, you get rid of that 1. You would just have the sum of the squares of the velocity vector components underneath the radical. And it'll be true. Okay, and last but not least, true or false? The flux of a vector field across a curve, not a surface now, a curve, can be computed using a line integral. This is a little bit hard, and I wouldn't expect you to know it, but I'm going to tell you true. And here's why. You're going to use Green's. Use Green's, the flux version, and that actually found flux of stuff across the border or boundary of that line integral. So flux was equal to this line integral, m dy minus n dx, and we found that we could, if it was a closed curve, we were able to do Green's here. It's a closed curve, and you could do that. All right. If you didn't have a closed curve, then you would use this line integral, and you'd have to parameterize and do all the substitutions and everything, but you still could get the flux across a curve. It would still work. Okay, and then finally, my final meme of the day, and then we're done today. I love this. I'll never be able to finish this. There's a Mebius strip, except it's a Mebius strip steak. Pretty cute, huh?
Wait, but he'll never finish it because it's like some kind of never-ending cycle.
Well, you know, once he starts on one end of the surface, he'll end up at the same spot that he started. I don't know. It's just kind of a play on the fact that a Mebius strip has only one side to it. It's kind of fun.
Oh, I get it now.
It's just cute. All right, congratulations. You are now done with surface and flux integrals. Yay!